Extra one? Yeah.
It's represents.
Oh, there you go.
When do we start partials? What section?
Oh, just like 15, I think.
Oh, wow.
Off the top of my head, I can't remember. Yeah, it takes a little while to get there. No, 14. Yeah. That's the neat part. All right, guys. Are there questions from homework stuff? Questions, homework.
When's it due?
Who has started 12:5 yet? All right, and how many guys have? Anybody have questions? Maybe more specific questions. What do you need for the equation of a plane? What do you need for the equation of a plane?
Normal.
Yeah, you definitely need a normal vector. Let's go this way. Let's go. We did all this business the other day about this here. All right, this is the idea. Let me stop there for a second. This is what you need to do for yourself. And at this level, you should already be doing this for yourself. But when you see this in the book and you see derivations, you have got to try the derivation on your own. You got to say, what step did I get lost in? You got to ask about what I got lost in this step. If you don't do this for yourself, you're not going to get everything out of this class that you could have. And it should just be automatic. When you see something like that, think about what the concept is behind that statement. I didn't write the statement and then figure it out. What happened in real life is we had a concept and we made a mathematical statement out of it. So what's the concept behind that statement? This is not really a unit vector. I should be here. Cha.
You've got a vector that's orthogonal to a line, and that line is a line on the plane.
So you have, and what is n defined to be though? I mean, this does end up saying, this says that this is orthogonal to some vector that's in the plane. But by itself, that's not the full picture though. Where do we get the normal from in the first place?
The triple cross.
What's the concept? You've almost got it. You're just being a little too specific.
Is it a vector perpendicular to the plane?
Yes. So obviously, if I say that the normal is perpendicular to any vector in the plane, I can pick any vector I want to, and this dot product would be 0. As long as that vector's in the plane. Okay, cool. But why does this define the plane? Because the idea of a plane is I just need a normal vector, right, and a point in the plane, and then it defines a plane. I move it, and now it's this plane. I mean, there's no question. If I said, where's the plane that would be right at the end of this marker, there's just one plane that's possible. And that's what it means to know what's sufficient and necessary to define something. And once you have what's sufficient and necessary to define something, you should be able to set up an equation that captures that idea. We did that with circles. What's the defining quality of a circle?
Radius.
Well, what about it? So the radius comes from the idea of what? A circle is a collection of all points that are equidistant from a center, right? So we say, okay, we got a center. Let's put the center at HK, and I want a circle to be all the points that are, and we'll call that distance R. That's where the radius comes from. It didn't come first. It came after we came up with the idea of what a circle is. And then you use the distance formula, and you get your standard equation of a circle. Right? But it started with the idea of what's the defining quality, necessary and sufficient. I'm going to say that sometimes. What must I have, and what's enough of what I need. I mean, I can define a circle in more ways than that, but what we said is sufficient, and what we said is necessary. I must have a radius, and I must have a center. I must have an idea of distance from the center. All right, let me stop there for a second. So here we start with the idea of, if I just add a normal vector to a plane, a vector that's perpendicular to every point in that every vector in that plane, then that normal vector somehow defines the plane. So this is what that says. So if I do have a normal vector, and when I dot it with any vector in the plane, it must come out to be 0. That's the whole idea we're using here, right? I'm not going to run through this again, but let me see. This was, I think they call it this ABC, right? Yes. And you dot it with, remember this was X, Y, Z, and this is X naught, Y naught, Z naught, blah, blah, blah. And eventually you get to AX plus BY plus, gather Z, CZ, and D was just the catch-all. Do you guys semi-remember that? Again, I got it in the book. You got to make sure that it makes sense. The more something makes sense, the more you remember how to do it. Now, now there comes all these problems. They give you all these problems, and in some problems they give you points, and in some problems they give you vectors, and in some problems they give you who knows what weird shit, right? But you always want to look at it as, what do I need from this problem to get the equation of a plane or whatever they're asking for? Same thing as in algebra when I say, what two things do you need for a line? What do you need for the equation of a line? That's one way to get what I need. What are the two things I need? But what do I get from 2 points? I get the slope, and I get a point. I can pick one of them, right? So what two things do I need, and why am I being so mean, sort of? 2 points, I understand that's all you need for a line, but what do you need specifically for the equation of a line? Slope, point. All right, sweet, right? So then they gave you all these freaking, I got a line that's perpendicular to this other line, and its x-intercept is 2 less than blah, blah, blah. Holy shit. And I try to teach my students, you just write, what do you need? You need a slope. Okay, how do I get the slope from all this crap they gave me? And what else do you need? The point. Okay, how do I get the point from what they told me, right? So that's what it's the same thing here, really. The idea leads to an equation, and I could use any version of this equation anywhere I need to based on what I know. So here, A, B, C, these coefficients, what does that relate to? Or, what is that exactly? That's the normal. It's crazy. So it's kind of freaky. I remember this when I was a student, when I learned this, and I said, okay, so this equation here, I knew more about that plane than I ever thought I knew. Now you can look back and go, well, what was the normal vector for this? 4, -1, 2. I love it. So that would be perpendicular to every vector in that plane. That's the idea. That's almost too nice to believe. But it's just like me give you this equation. And the slope is 4. Why? Because it's in the right place. Okay, well, normal vector is 4, -1, 2. Why? Because those numbers are in the right place. Because this is on the back of a lot of freaking work. Right? Okay, maybe. So a lot of what we do in this class is in 3D, I know that, but you can relate it to ideas from before. Totally. Okay. So you need the normal point, and you need, the normal vector, and you need
a line segment.
Yeah, because, so here, so if I give you a point in the plane, is that sufficient? In fact, there should be some problems that asks you, blah, 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 blah. Yeah, there you go. Number 24, for example, gives you a point with a normal vector, blah, blah, blah. Okay, maybe. So now a really good question would be, okay, how would you work a problem like that? So let me see. Let's see if you guys can do this. So I'm not going to give you 24. Let's say I have the plane with n gather equal to -1, 4, 2. That includes point. What you got, Jeff? I don't know. 2, 3, -1. Can you come up with the equation of that plane? And real quick, why would that not be sufficient? That is necessary. I must have a way to figure out the normal vector, or you just tell it to me directly. But why is the normal vector not sufficient? It's necessary. You got to give me a way to get it. But why is it not sufficient? Why is it not enough?
Need or not. You need something to...
Why though? Tell me visually why. Like tell me geometrically why.
Where it stops.
Yeah, I love it. So if I only had a normal vector, well, where on that normal vector is the plane? I kept saying it was like the tail end, but I have to tell you that. The point at the tail end is on the plane, bam. What if the point in the middle is at the plane, then the plane is here? Okay, I like it, cool. So you need the normal vector, sort of a directional thing really, right? Like perpendicular to the real direction, and then a point to tell me it's sort of related to the y-intercept, right? So you need a direction and a point. Holy shit. Now it's just a question, can you put this all together? Can you give me the equation of the plane from this? Take a minute. Work together? Or by yourself? No, because like, dude, I already tried. What do you want? They should have, and if you have your book with you, they should have an example. I'll give you a little hint, guys. There's something I've skipped over here before you get to this that is actually a more useful version of the equation. No, it's too far back, yeah.
But that's what leads us to AX plus BY.
Totally,
Okay,
yes.
good.
It's like John Madden going, I'm going to executive quarterback right around here. Thanks, Jeff, for that. This is N. So I know A, B, C, for example, right? This is what in general? The point that I give you is what related to the work we did? X naught, Y naught, Z naught, right? It's the point. That's anytime you have a subscript, that's a specific given thing. It's not anything it wants to be. So the point that I'm given so you're just not familiar. Of course you're not familiar with working with this. But if you feel like you're never going to get it, that's a little crazy. You just got to work with it and get used to how these things come together. If I just give you this, all right, well, that's this, which is that. Now, what do I put in here? If I wasn't sure what to do after this, what would I fill in here? What is R more explicitly?
XYZ.
Yeah, XYZ. So what's R minus R naught?
X minus 2, Y minus 3, Z plus 1.
I like it. So now you can plug in the specific things and just, there's two ways you can go with this really, but it's not, well, it's sort of two ways. Remember, there was that parametric way of doing well. That's for lines. This guy would be what? What's the dot product? So let's do, let's put in the specifics. -1, 4, 2. X naught, where'd it go? 2, 3, 1. And yeah, once you do this, I don't mind you doing this actually, because it's really going to show you why things fall into place. But now you see a shortcut to this, maybe. Yes? Yes. What's the dot product do? It's very simple, very, very nice when you got both the vectors and all the components.
2 minus 4 times X plus.
-1 times X minus 2 plus 4 times Y minus 3 plus 2 times Z plus 1. And of course, the thing I'm leaving off here is equals 0. So then what's the shortcut? Sort of like related to, this is really a shortcut from, setting up the slope equation, then multiplying it by the x's and blah, blah, blah. Now I can see a shortcut. It would be a times x, and they write this in the book. If you really can see how that's very similar to the equation of a line. I have A, B, and C. Why are they coefficients like the M was? Because A, B, and C control direction in a sense, right? And then inside are all your offsets from the origin for the point that you're using. Okay. All right. I mean, there's a lot of similarity between. This is the most general version of the formula for a plane, really. The D thing is just not the most immediately useful for what most of the equations I'm going to be using look like. I'm going to be given points. I'm going to have ways to find normal vectors. That version of the formula is probably the most useful. Okay, maybe. So that's how you look at these problems. You say, I know what I need for the equation of a plane. How do I get those things that I need from the situation they set up for me? That focuses your attention. How do I get the normal vector? Start there. Get that completely done. How do I get the point? Do they give me a point, or do I have to figure out a point? Or do they give me 7 points, and I can pick one of them? Doesn't matter. If they give me 7 points in a plane, which one must you use? Any of them, because I just need a point on the plane. Cool, I like it. Maybe. Does that help at all? I don't know. Did you have any more specific questions? No? You're like, dude. I just want to change your focus a little bit, because when you have a problem, when you have a section like this, and it seems like there's a ton of shit, you have to distill it. I need you to understand what goes into these equations, but then you can make the practical side of it and go, we did a lot of stuff to get the idea, and we worked the idea out, and we have several different versions of the idea. What do those versions all mean? What do they need from me to be able to just to use them? Right? So there's the conceptual side, and then there's the nuts and bolts side, always. Yeah?
Can you go through 12?
12?
Yeah.
Would you say that for any number he said? No, I don't know.
Those two were the ones that affect the most.
All right. So here they give you 2 planes, right? This is number, 12, no, this is 12.5. Number 12. And they went into the line of intersection of the planes. Now, some of you guys, I don't know, depending on how much you've worked with matrices, remind me again, anybody already took linear algebra? Anybody? So a few of you guys are like, well, I got a way to do this. But what have you tried so far? You asked me this question, right?
Yeah, I set an equal to eliminate a couple things, but then I think, if I remember correctly, I had to somehow plug that back in. It didn't quite work out, so I just it's clear that I was fine exactly.
Okay, cool. I like it. So you've actually done this problem already, even if you haven't done linear algebra, believe it or not.
So one of them equals 0 since you only have 2 equations.
You could. So what you were saying, let's investigate your line of thinking. Like I could kill the x's, for example, right? Between the two of them. Right, and this is what I mean about matrices. It's sort of like putting these into a matrix and start to row reduce them. Right? And let's see where this leads us.
I was kind of thinking, like when we do intersections of lines, it's easy because you just eliminate one of the parameters and then you get one of the other one is this, and then you plug it back into the original.
Exactly. But real quick. Like if I had this, if I had x plus y equals 4 and 2x plus 2y equals 8. Right? What's the equation of the intersection of these two?
X plus y equals 4.
Yes, x plus y equals 4. I like it. So you'd say x equals t and y equals t minus t You could do it, Jeff. 4 minus t, for example. And now we know, this is kind of silly, I just said what this is, but what is this? Is it a plane? Is it a space? Is it a dot? It's a line because it takes one parameter. It's like a one-dimensional thing. Let me be more specific. So it's a line, and if I have one parameter, it means it exists in one dimension somehow. That dimension could curve. That's one way to look at it. Please, dear God. And to me, it just makes it, when we get there, we'll talk about different ways to look at it. But to me, that's the way that makes the most sense. So I could do a similar thing here. I can't even remember I know there's an example in the book, but I can't remember what they do. If I just change all these signs, right? And then add them, what do I get?
3y is 4z. 2z.
Cool. Right. So then I get, for example, I get z equals negative 3/2 y. Is that cool? So then what would x equal? Let's use this one. Bring that back to normal. X would equal y minus z plus 1, right? But now I know what y is in terms of z, right? So now I can get x in terms of z. So now z is like my t. Do you guys see that? This is one way to do this. I don't know how far you got or why you thought it was the wrong way to do it.
I think I just kind of stopped and did this time.
Gotcha. Okay. I don't know why you're being mean to yourself and saying you must get it done now. What versions of a line are there? What for equation of a line? We have a couple of options. We have the one that looks just like y equals mx plus b, except the inputs are vectors, which is actually a really beautiful thing if you let it be. Wait. This is the kind of This is the kind of thing you have to do for yourself. You need to just every now and again just say, what do I know so far? What's the equation of a line? How many ways do I know how to write the equation of a line? How many ways have we talked about? What's the vector way to do it? The vector value, the vector definition. You gotta love that TV shit. It makes it easy to remember. Where V is the
It's a parallel vector.
yeah, and we gotta be careful. I appreciate when you say slope. It's like the slope. Slope is a less general term. It's the directional vector, right? It's the direction. Because now slope sort of inherently means like 2 dimensions. It doesn't have to mean that, but I want to be more general in how we discuss things. So this contains information about what direction I want to go in, and this is where I start in a sense, right? The starting point doesn't matter because t could be negative or positive. I'm going to go in both directions forever. Let me stop there for a second. What's the other main version of how to write the equation of a line? No. Any dimensional line. Or let's say 3-dimensional line. 3-dimensional line, let's be careful. This is any dimension. This is any dimension. You guys understand? That's any dimension. Alright? Now what's the one specific, another way to write it if it's in 3 dimensions. There's one other way to write it. And remember, so watch. What is this again? X, Y, Z. And what they use here, which is kind of funny, but it actually sort of makes sense. ABC. So they use the same thing for the normal vector for a plane, and the reason they do that kind of makes sense because they both control the direction, the slant or whatever you want, the direction, the basic direction of it. All right, let me stop there, let that sink in. You've got to stop trying to memorize everything. Now, if you're able to, great. If you're not, if you know this is pretty easy to remember. It's not that many steps away to get what I'm talking about right now. I mean, look at this. What is this? So let me fill this in. So what do I got for the components? What do I got for the x's?
X equals x naught plus
And if I solve for t, I get...
x minus x naught equals.
And if I do that continuously, yeah, there we go now. Right?
Those are the reflections.
Say, sorry?
They're called, there was a special name.
Symmetric equations.
Symmetric equations, yes. All right, I like it. And this one here, these are where I think they call this the parametric equation. They should. All right, cool. I like it. It always depends on which book we're currently using. All right, is everybody decent with what's happening here? I mean, you should be able to recapture any version of an equation of something by starting at the basic principles of it. This is the basic principle of a line in any dimensions. So if I want to talk specifically about 3, I can use this to get to it. Real quick. I keep saying real quick, but if I was in 2 dimensions, what would this look like? I got to start. Yeah, x naught, y naught, plus t, ab. So I get x equals x naught plus ta, and y equals y naught plus tb, right? Let's go there for a second. I don't know if you're at home. There you go, you can see it now. So what can I do with this here? Again, I can solve for t, and of course I'm going to get what? Now watch, this is interesting. So I get y minus y naught over x minus x naught equals b over a. So what am I going to call b over a? What letter am I going to give it to work back to algebra? M. Holy shit. Yes, maybe, sort of. So if I call it, so y minus y naught equals m times x minus x naught. I don't know if you guys remember, they gave us a line, and I showed you how to make a vector out of its slope. This is the reverse of that. We started with a vector, and then now we recaptured the slope. So remember that? I don't know if you guys remember that. If you know the slope, you know the y piece and the x piece, you can make a vector out of that. This is just the reverse of that. In 2 dimensions. 3 dimensions, you can't recapture that. Any dimension above 2 is too bad for you. There's just too many sides. Look at that equation. That has 3 sides somehow. A 3-sided equation. That might be the first time you've ever seen that. I don't know. That is not easy to work with. I mean, it doesn't immediately make a ton of sense. I understand that. But if you go back to 2 dimensions, you can see why it captures what we know already. And this is the same idea that I can use to capture what we know, but to capture what we don't know. I don't know how 3 dimensions is supposed to work if I'm not used to working with 2. All right, maybe. Always hopeful. I'm not big on giving you recipe-ish ways to do things. Every now and again I will, of course. You need some of that. You need a little bit of that. But you got to start with the idea of something and then work from there. The more you can do that, the further you can go in math. The less you can do that, there's a stopping point for you. I'm sorry. All right? Some of you guys are like, dude, I'm about where I want to stop. So I understand. All right. I won't take that personal. Calc 3, hey, that's awesome. Can't blame you. This is as far as you go. I love it. Just want you to know you're missing out a lot. It's too bad for you. All right, and I don't know if I captured every question, but did we finish that one? We sort of did. I mean, I think I went there, and then coming back to this, what did I say here? Yeah, so if z equals that, and so now my y is going to act like, I think I said it the wrong way around earlier. So x equals y minus, so now plus 3/2 y plus 1. So x would be 5/2 y plus 1. Now this is not the only way to do this. Some of you guys did this a very different way. Possibly, right? So I can write, so what do I got so far? Let me collect what I got. I got x is 5/2 y plus 1. I got y is, and that's a separate thing, right? Y is y. And z is negative 3/2 y. So let me change a little bit. We normally just use, this is where we bring t in. And I don't know if you guys see, the reason why we bring t in is just to refocus our attention on t as its own number. If I make it y, it seems to have other meaning or something. T is its own little single parameter. The t-axis, has anybody ever said that to you, the t-axis? The t-axis is one you can't see when you normally draw parametric equations, but there is a t-axis. And that's why I say this is linear. Because it only requires one parameter to describe it, and it's, it's in a plane, it only requires one parameter to describe it. Maybe. So the dimension curve. So where's the t-axis? It's curvy. We don't have to go too far down the road. I don't want to freak you out. We're not going to do that. We're not going to have, here's my x-axis and here's my y-axis. Now, what's that point? No, we're not doing that. I know somebody right now is like, so that point would be, let me draw my coordinates. Oh my God, no. It's just the idea. It's the idea of it. Okay. I don't blame you. All right. So, I mean, there's other ways to do that problem. Who else did the problem a different way? There's a different. This is kind of like based on older ways to do it. Nobody wants to speak up. I understand.
I think I said zero and
Yeah, did they give you an example like this?
I think so. They did something kind of like
But they did the whole say C equals 0.
Yeah.
Which example is that? Let's see.
maybe I found that online.
Oh, here we go. 7b. Example 7b.